Hi, I'm Tom from Weizmann Institute, and I'll be talking about a hierarchy theorem for interactive proofs of proximity. And this is a joint work with Ron Rothblum from MIT.
Why is Cartman an interactive?
Well, you want him to respect the authority and hierarchy. And so the plan for the talk would be quite straightforward. We'll begin by discussing what interactive proofs of proximity are, why I think we should all care about them, and also let you know a bit of what's possible and not possible using them. Then I'll present the main result, which basically says that more interaction equals more power. And finally, I'll show you a couple of applications to general interactive proofs and general complexity theory. Okay, so what are interactive proofs of proximity? So one way to think about them is taking property testing problems and considering the notion of proofs within this framework. So generally, when we're dealing with property testing, we are given some input x, and we have the task of deciding whether it has a certain property pi or whether it is epsilon far from having this property. And we have a tester or a verifier which makes this constant or small number of queries to the inputs to the end of making this decision. Now, what are interactive proofs of proximity? We simply add a prover here, which is the input entirely. And then the prover and verifier are allowed to communicate. The verifier, as before, queries the input, and then it has to decide membership in the language or in the property. And the usual completeness and soundness applies, in which we say that if this is a language, an input in the language, then there exists a prover strategy that we would accept always. And otherwise, if we are epsilon far, then with high probability we will reject. So this is the definition. Now, you should ask me, why should we care about interactive proofs of proximity? Now, I'm not trying to go against Timon and Tumba's motto, but I really think that we all should care about them. And let me try to convince you. So the most basic reason is that it allows us to understand the power of proof for property testings. Similarly as why we studied NP proofs or PCPs with respect to polynomial time computation. But also, if you think about it, say you're interested in developing some interactive proof system that works in sublinear time, and your verifier cannot even read its input, then we have to make some sort of compromise, and the relaxation using testing is quite a natural one. Also, it can provide an illuminating lens to general interactive proofs, as I will show you in the applications. So it can teach us beyond the world of property testing. And we have some very nice applications to delegation of computation. And in general, even though this notion was introduced only a couple of years ago, there are plenty of applications to coding theory, PCPs, communication complexity, cryptography, and data streams. Okay, so now that hopefully I convinced you this is a worthy notion, let me try to give you an intuition or an example of how proofs can really help testing algorithm. So this is my favorite example because it's the easiest to explain. It's by Fisher, Goldhirsch, and Lachish, and it tells us the following. So say we have a palindrome, like taco cat, which is my favorite palindrome, by the way. Palindrome is a word that reads the same from the beginning and the end, and testing it is very easy. It can be done using constant number of queries. You just query a location, the same location from the beginning and the end, and test for equality. However, what happens if you have another palindrome, like UFO tofu, and we're given the string that consists of both of these, and we want to know whether this is a string that consists of two concatenated palindromes. In this case, it was shown that the query complexity suddenly becomes much harder. It becomes square root of n. But using a very short proof, namely a pointer that says where this palindrome ends and this one starts, we can reduce the query complexity to O of 1 simply because this reduces to two independent problems of palindrome testing, which is easy. Okay, but this is just the beginning. Interactive proofs of proximity can do much, much more. For example, even without interaction, so if we're giving just non-interactive proofs of proximity, then we can test in sublinear time any language accepted by read-once branching program or context-free languages. We know that if we add interaction, then suddenly you can be exponentially stronger than what we could without interaction. And in fact, with only 3 rounds, we can handle any CSP problem. For example, Trisat, yes?
5 minutes.
Oh. Okay, and if we allow constant round IPPs, then we can get some bounded time and space computations. And if we allow polylog rounds, then we can pretty much tackle all of NC. And yes, there are 2 Rotblums working on this. So this way you can know which is Guy and which is Ron. Okay, and now if you look, then there is kind of a trend here. Notice that here we are without interaction, and here we are with plenty of interaction. And you kind of see that the results, naturally, the more interaction that was allowed, the larger the classes that could be handled. And this raises the question, does the power of IPPs grow with the number of rounds? And this talk is about showing that it does, and answering this question. So our main result shows a hierarchy theorem, which, roughly speaking, says that more interaction will give you more power for the IPPs. So what do I mean by that? We show the following. We show that there exists an explicit language such that for every constant R, we have an R² round IPP with some verification time, let's say T. And any R round IPP for this language would have to do, say, 2 to the 100, where the exponent here is arbitrary. And so this gives us this hierarchy of lower bounds and upper bounds, which basically says that you have to do a certain amount of rounds in order to outperform the lower bound. And I want to point out that, notice that there is a gap here. So the upper bound has R², and the lower bound has R. And this is, in fact, an open problem, whether we can narrow down this gap. And we strongly believe that it's possible. In fact, in an upcoming work, we show that under an assumption regarding matrix rigidity, we can show the right gap here. But I would like to bring to your attention that it could be nice to do it without any assumptions. And also, what actually happens here is that the constraint that the round complexity has to be constant, it only applies to the lower bound. So in a sense, we can, in the upper bound, use logarithmic number of rounds. In this way, we can get sub-exponential separation between the power of constant round IPPs and super constant round IPPs. So I won't have enough time to talk a lot about the techniques. So let me just tell you in a couple of, in 2 sentences. And if you're interested, then there is a poster session soon in which I can tell you in much more details. But our upper bound is used by, we construct this, a new construction of a certain type of interactive PCPs, which exploit the structural properties of the low-degree extension code. And for the lower bound, we showed that actually if we are giving a language, certain type of algebraic language, in particular the language that we use, then we can think about IPPs as a distribution over small depth circuits with parity gates. And then we can lift the Razborov-Smolansky lower bound and obtain a lower bound for IPPs. Okay. Now for applications. So one application that we can give is that we can show that the standard round reduction due to Babai and Moran is actually optimal among all black box transformation. So let me just start by telling you what are black box transformations. So black box transformations are transformations that take an interactive proof and create a new interactive proof, where the new interactive proof, so the new verifier can only make Oracle calls to the original verifier, and the new prover can only make Oracle calls to the prover strategy and the verifier strategy. And in fact, it turns out that most of the transformation that we use in the literature for interactive proofs are black box transformations. And this shows that we can't really outperform Babai and Moran here. And I think that the interesting part is that we started with a statement that deals with testing and with proximity, and we left it to get a general result about interactive proofs of proximity, about interactive proofs. And the last application that we have, I'll just say a sentence about it, is that we show that there is some profound connection to the algebrization framework of Aronson and Wigderson, which shows barriers to proving certain problems in complexity theory. And I'd be happy to tell you about it more in the poster session. So that's it. Thank you.
Question?
You mentioned that under an assumption you can get the right gap. What exactly is the R versus R plus 1?
Yeah, exactly. It means that each round, each additional round would give you more power.
And what do you get then as a gap? I guess it's no longer 100, or is it still?
So then the bound, it's like you get the complexity is theta of n to the 1 over r. So it's not arbitrary as in our case, but we believe that this is like the exact bound.
All right, let's thank Tom again.